When working with microscopes, one common question that you might ask yourself if you're visualizing a specimen is how many times has this specimen been magnified so that I can see the image that I'm looking at now? Well, the answer to that would be total magnification. It's very easy to calculate. To calculate total magnification, all you need to do is take the power of the objective lens, which is whatever one you have clicked into place, and then multiply that by the power of the ocular lens, which is usually a standard number, usually 10 for our microscopes. So if you are working with a microscope and you have the very first objective, the smallest objective clicked into place, it magnifies by 4. Your ocular is always a standard 10. So then your total magnification would be 40x. We always use the x as a unit of measurement for magnification. Definitely in our course, because we're working with microorganisms that are so small, we often have to go to the highest level of magnification on our microscopes, which is the oil immersion objective. That one magnifies by 100, and again our ocular is a standard 10, which means your total magnification would be 1000x. So these numbers are the standards for our microscopes. They can change depending on what type of microscope you're using, but as long as you remember the formula, it's just the power of the objective lens times the power of the ocular lens. If you multiply those two together, whatever those two numbers may be, that gives you the total magnification. While magnification is extremely important in microbiology because it makes the specimen larger, it cannot be successfully accomplished without proper resolution, because it does us no good to make an object larger if that object is blurry. So resolution is the capacity of an optical system or a microscope to distinguish or separate between two adjacent objects or points from one another. So basically, it's the ability to see different bacteria as actually different cells versus one just big blob of a bunch of cells all pushed together. And we can kind of see good versus bad resolution here in this image. So we have bad resolution up here. We can see individual structures, but you can see they're quite blurry. Down here, we've achieved we've achieved resolution, so we can see them magnified, and then we can also see them clearly and see the separate, distinct structures. How we achieve resolution in micro is by using the oil immersion lens and immersion oil. What immersion oil does is when you apply a drop of immersion oil to the slide, it collects extra light and then shines that light directly through the specimen, which allows it to illuminate the image in an enhanced manner. So a lot of times if you're working with a bacterium under the microscope, if you have it under the third objective, which is the high dry objective, then it'll kind of look like this. You'll be able to see it, but not very clearly, and it'll look quite blurry. But then once you take it to the oil immersion objective, which is the fourth one, and you put down a drop of immersion oil, you get that extra light that shines through the specimen, and the image becomes much more clear, like what we would see here. And that means that we've successfully achieved resolution. So resolution is basically the ability to see an image clearly. And the last principle of microscopy is contrast. So contrast refers to the darkness of the background relative to the specimen. So ideally, we just want to have a substantial difference between the specimen and the background. So here the background is white, which is typical for using a clear microscope slide. And then the specimen or the bacteria are pink and purple, so they're colored different colors. But that allows us to achieve that contrast against a white background. Naturally, bacteria really don't have any type of color, so if you try to just put bacteria on a clear microscope slide, you don't get good contrast and you wouldn't be able to see them very well. So in order to achieve contrast in micro, we actually have to stain the bacteria purple, blue, pink, whatever, and that allows us to visualize them against the background. So staining is a way that we achieve contrast in micro. So with that, we're going to go on to talk about how to prepare microscope slides and then eventually get into staining. So when you prepare a microscope slide, you have two options, and you need to ask yourself, do I want to do a living preparation, or do I want to view dead bacteria? With living preparations, they're really only done in situations where you want to see if the bacteria are mobile or not, if you want to see if they can actually move. This can be done by utilizing a wet mount or a hanging drop preparation. Both of those are just types of living preparations. Really all it is taking a glass microscope slide, adding a sample of water or broth, adding bacteria to that sample, putting a cover slip over it, and looking at them under the microscope to see if they're mobile or not. If they're moving, that means they're mobile, which is a good indication that they obviously have flagella. If they're not moving, that typically means they're non-mobile and they likely do not have flagella. So the only time you would ever really do a living preparation is, again, if your intention is to view mobility, in which you would have to keep the microorganisms alive. The majority of the time, you are going to do a slide preparation in which you are going to prepare dead bacteria. So you won't be able to view any type of active movement, but what we do is we kill the bacteria on the slide, and then we stain them. And then after staining, we're able to observe different things about the bacteria, like things with their cell wall, if they're able to produce endospores, that type of stuff. So when you're asked to do a smear preparation, that is essentially viewing dead bacteria under the microscope and then eventually staining those bacteria. So with a smear preparation, what you'll typically do is you'll have a glass microscope slide. You will add some type of liquid to it, such as water or broth. Then you'll add a sample of the bacteria to the liquid, and then you'll let it air dry. And then you have to go through a very important step called heat fixation. Heat fixation is always done when you're doing a smear preparation. What heat fixation is it's simply applying heat to the slide that now contains the specimen. And that's what we're looking at here. This slide is going through heat fixation by being passed through the flame of a Bunsen burner several times, but you could also set this slide on a hot plate for 30 seconds or so, and that would also achieve heat fixation. But heat fixation is essentially just the process of applying heat to the slide, and what it's going to do is accomplish three things. One, it's going to kill the microorganism that you're wanting to view. Two, it's going to stick the microorganism to the slide, because on our next step we're going to go through staining, which requires a lot of rinsing, and if the bacteria are not stuck to the slide, then they'll just rinse down the sink. So we need to heat fix in order to get them to stick to the slide. And then the third thing that heat fixation accomplishes is breaking down the membranes of the bacteria so that they can absorb stain. Sometimes bacteria are resistant to stain because of their protective membranes, but what the heat does is it kind of loosens those membranes up a little bit so that they can readily absorb the stain. So once you've done your smear prep and you have your dead bacteria on the slide and they've went through the heat fixation process, in order to visualize them now, you have to go through staining, because remember, bacteria really don't have a natural color. So in order to see them against the white background of a slide, in order to get that contrast, we have to stain them. So a stain is really a process where you apply dye to the specimen in order to give it color. There are different types of stains or different types of dyes. There are basic dyes and acidic dyes. Basic dyes have a positive charge, and since bacteria all have a negative charge, there is an attraction. Basic dyes with their positive charge will always bind to bacteria since bacteria have a negative charge, and they will stain the bacteria. The opposite of a basic dye is an acidic dye. Acidic dyes have a negative charge, and since bacteria also have a negative charge, there's a repulsion. Acidic dyes will never actually stain the bacteria. They can't because of the repulsion, Instead, acidic dyes will stain the background behind the bacteria. So it's kind of like stars in a night sky. The background would be the acidic stain, which would be the night sky. And then the cells would be like the stars sticking out against the night sky or the dark background, which that would be the bacteria. So when you're asked to do a positive stain, you typically do need to use a dye that's going to bind to the specimen and give it color. So in positive staining techniques, you are wanting to stain the specimen, which means you will need to use a basic dye. Basic dyes have those positive charges that will be able to bind to the negatively charged bacteria and give them color. Most of the time we'll be doing positive stains, which stain the bacteria and give them color with that basic dye. Negative staining procedures are used sometimes, not nearly as much as positive staining procedures, but in a negative staining procedure, your goal is not to stain the bacteria. Your goal instead is to stain the background, and then the bacteria will be colorless, sticking out against that dark background. The only time we really do a negative staining procedure is if we're working with bacteria that can't be heat fixed. Some bacteria, if you take them through the heat fixation process and apply heat to them, they shrivel up and you can't see their natural arrangement. So for example, the Spirillum bacteria, that are those loose waves, if you put them through heat fixation, they would shrivel up into a little ball and almost look coccus. So typically when we're working with like Spirillum type bacteria, we will utilize a negative staining procedure, which doesn't require heat fixation. But the acidic dye wouldn't actually stain the bacteria. It would stain the background behind the bacteria, and then you would see these little clear squiggles everywhere, which would represent the Spirillum bacteria. And this is just an example of what this looks like. So over here, we have a positive staining technique where a basic dye, which was probably crystal violet, was used to stain these bacteria. But you can see how the bacteria are colored with the basic dye, and then the background is white, so we have that contrast. And then over here, this was a negative staining procedure. So this was a dye called nigrosin, which is an acidic dye. So because it has a negative charge, it was repelled by the bacteria, and it only stained the background. But then we have the bacteria kind of sticking out against that dark background as colorless units, so we still have that contrast. So we're going to tend to focus more on positive staining techniques, which are the ones that require basic dyes in order to stain the bacteria. Those are the ones that are most often used. So there's different types of positive staining procedures. The simplest one is a simple stain. This is the one we always start out with. A simple stain, you only need one dye. It's going to stain all the bacteria the same color, and it's just going to show you general characteristics like size, shape, which would be something like is it coccus, is it bacillus, and arrangement, like is it in clusters or chains or by itself, whatever. So over here we have what appears to be a sample of Staphylococcus that was simple stained with a basic dye called crystal violet. So all the cells are purple, and we can just kind of generally view size, shape, and arrangement. And then over here, it looks like maybe we have some E. coli that was simple stained with a pink basic dye, likely safranin. Again, just to visualize kind of standard size, shape, and arrangement. Once we kind of master simple staining, which is just, again, using that one single dye to view size, shape, and arrangement, then you can advance on to differential staining techniques, which are much more complex.